Okay, good morning. Welcome to today's lecture. So, we were discussing a solution of linear equations in the last class. So, let us get started with that. So, this is a solution of linear algebraic equations. So, what we noted was there are two important characteristics that these linear equation set has. The first one is that the matrix, the resulting matrix is sparse, okay. That means there are a lot of zeros in the matrix that we assemble, and then the matrix is sparse, and also it may have a banded structure, right. That means all the non-zero elements, right, all the non-zero elements could be aligned along the diagonals of this matrix, right. So, non-zero elements along the diagonals, okay. And we also noted that if we have nonlinear problems, we have nonlinear diffusion coefficient or source terms, then the coefficients that we get are only provisional, right. So, these are the two main properties that we kind of noted for the matrix A, okay. So, there are mainly two different methods that can be used to solve the system of linear equations. The first method is a direct method, and the other one is an iterative method. So, let us look at each of the advantages and disadvantages for each of these methods. So, in the direct method, what we do is essentially once you assemble these equations, right, you have a system of linear equations that we can write it as A phi equals B, right, where A is the coefficient matrix, and what is phi? Phi is the vector of unknowns, right, that is what we set out to solve. So, phi is your phi 1, phi 2 and so on all the way to phi n. So, this is the vector of unknowns that we want to solve, and B is what? B is a known right hand side vector, right, essentially it is a known right hand side vector that could be some B1, B2 all the way to Bn and transpose, okay. So, this is what we set out to solve, and then in the direct method you essentially invert the matrix, okay. So, that is what you would use, you invert A, essentially you want to solve for phi equals A inverse P, okay. But we realize that inversion is a very, what is it, a very easy process or cheap or expensive? It is expensive, right, computationally it is expensive. For example, if we have a system of n unknowns, what would be the size of the matrix A? If we have n unknowns, n cross n, okay. So, we have n by n, and what would be the number of operations involved if we want to invert this matrix? Order of n cube, okay. So, that is a lot. If we have 1000 cells, then you are doing a billion operations, right, 10 to the power 9. So, which is very time consuming, and also we need to store all n square elements, right, because out of which many of them could be zeros. So, we will be like storing a lot of zeros as well. So, store all n square elements and also do a lot of operations. So, this is not a good way, at least for the matrix that we get in order to solve for phi, okay. So, not a good method, because it is not considering the sparsity or the banded nature of the matrix that we have, okay. So, that is why we do not kind of prefer direct methods. So, that is why the direct methods are not used in simulations of, let us say, fluid flow and heat transfer. So, in CFD today, okay. That is because the direct methods will not take advantage of the sparsity and banded nature of matrix A, okay. And also of course, we kind of discussed that the matrix A, the coefficients are provisional if we have nonlinear diffusion coefficient or nonlinear source terms, in which case we probably do not need to invert this matrix exactly, okay, because the coefficients are anyway provisional. We could probably get away with getting an accurate answer, like an approximate answer, instead of getting an exact answer, okay. So, that is another motivation. So, essentially we so may not need an exact solution for A inverse, because the coefficients are anyway provisional, okay. Okay. That said, we would kind of go about to iterative methods. Iterative methods work on guess and correct the solution. So, the philosophy is basically guess a particular solution and then correct it and then keep doing it, okay. That is the philosophy for iterative methods. Now, what are the examples of iterative methods that you know to solve for A phi equals B? Jacobi, okay. So, Jacobi and Gauss-Seidel, okay. So, Gauss-Seidel, okay, and you have variants of this using relaxation and things like that, okay. Somebody said tridiagonal as well, right? Tridiagonal algorithm as well. So, how is it different from Gauss-Seidel? It will be the same, right? It will be the same. You just have a decomposition and then you would do it, okay. Okay. So, well, it will not be the same in the context of Gauss-Seidel, right, because in Gauss-Seidel you have an iterative method, whereas a tridiagonal one would be kind of a direct method, but it will take advantage of the banded nature and the sparsity, okay. We will come to the tridiagonal matrix method later, okay, once we kind of finish this discussion on iterative methods, we will come back to that. Okay. So, essentially you have a guess and correct philosophy for these iterative methods. So, what we do is we start off with the equation that we have derived. So, the equation we derived was AP PP equals, let us say if you are looking at a 1D problem, A east phi east plus A west phi west plus some source term, we call it let us say B, okay. So, what we do is we essentially rewrite this equation for the unknown. The unknown is the unknown for the P itself, right, that is what we are trying to solve, okay. A phi P equals A east phi east plus A west phi west plus B upon AP, okay. We rewrite this equation for the unknown phi P. Now, what we do is we guess phi values, okay, over the entire domain, okay, and repeatedly solve or sweep the equation 1, okay, which is this one. So, essentially you repeatedly apply this equation to cell after cell, okay, and then you keep sweeping it, okay. By sweeping I mean we just go from one point to another point, okay. That is what we do in a Gauss-Seidel or a Jacobi method, okay. So, how does it work? Essentially what we are talking about is we have let us say several cells, okay. So, we start off with so these are the cell centroids. So, we apply for the first point phi P would be equals phi 1, let us say if we call it as 1, 2, 3, 4, 5, 6. So, phi P equals phi 1. So, you would guess the values of phi 2, okay. So, you would guess some values initially everywhere, okay, and then you would also guess the values on the boundaries, or this could be already given depending on the boundary conditions. Okay. So, using that you have written one equation for phi p, right. You got a linear equation, algebraic equation for phi p or phi 1. You would rearrange that in this equation form of 1, and then you would solve for this using the guessed values on the right hand side. Okay. These are all the guesses, and you already know what is b and what is ap, and the coefficients are all known. Okay. So, essentially solve for phi p, and then you go to the next cell, cell 2, okay, and then you again solve for that corresponding equation for phi 2 in terms of phi 1, phi 3, where you would use phi 1, phi 3 values, right, and you would solve for phi 2, okay, and then you go to phi 3, use the guessed values of these two and then solve for this. Okay. So, that is what we do in Gauss-Seidel. Now, in Gauss-Seidel, the unknowns to the right hand side, okay, or to the direction which we are sweeping are all guessed values. Okay. So, these are all guesses, let us call it G, and then all the unknowns that we have already traversed, they are all updated. Okay. Let us call these are updated. So, U, let us say if you are solving for Q4, you will have updated values for Q3, phi 3, phi 2 and phi 1, right, whereas the unknowns for 5 and 6 would be phi 5 and phi 6 would be the guessed values. Okay. So, as soon as you found a value for a particular cell, you would update that with what you have found. Okay. So, that is what you do in Gauss-Seidel. So, essentially in Gauss-Seidel you update the cell values as soon as you calculate, okay, as soon as they are calculated. Okay. Now, now that brings out the difference between Jacobi and Gauss-Seidel. In Jacobi you would not update them, okay, you would leave, you would still use the old values for all the neighbors, although you know that you have already calculated an updated value. Okay. So, in Jacobi old values of phi of neighbors will be used, and all the new values will be updated in one go after you sweep the entire domain. Okay. So, essentially once you, so after the sweep we update phi values. Okay. That is the difference between Jacobi and Gauss-Seidel, otherwise it is pretty much the same. Okay. You go from one cell to another cell and then keep updating this. Now, okay, so you may have a question like, then why do we need Jacobi, right? We should, so actually it actually started in the other way around. Okay. It was Jacobi the first method, and then Gauss-Seidel was an improved method. Okay. The way it was found that people started using Jacobi was proposed, and then method was used, and then they realized that if you use the latest updated value, the convergence has the convergence rate has doubled. Okay. So, essentially you would get the solution in half the number of iterations you would need for Jacobi. Okay. So, that is how this was kind of accidentally found, and that is how the Gauss-Seidel kind of came about from Jacobi method. Okay. Of course, if you look at it from memory point of view, which of these methods do you think would require more memory if you compare these two? Jacobi, because you have to store the old values and the new values, whereas if you have Gauss-Seidel, you just have one array of phi, right, and then you can just keep updating it. Okay. So, in that sense Gauss-Seidel is faster, requires lesser memory compared to Jacobi method. Okay. All right. Now, unlike direct methods, now these iterative methods only require they do not need a storage of the full matrix, right. All you need is you need to store all these coefficients, that is A east, A west and AP and B per cell, that is all, right. So, you do not need. So, in the direct method we have stored n square floating point values, right, whereas in the iterative method how many do we need? We have AP, A east, let us say we are talking about a 1D problem, and B, right. We have these 1, 2, 3, 4 coefficients per cell, and how many cells do we have? N cells, right, we have n cells. So, how many do we need? 4 n, that is all, right. So, this is much smaller compared to, so if you have let us say 1000 cells, you just need 4000 floating point values to be stored, whereas in the direct method you have to store 10 to the power 6, right. So many elements have to be stored. Now, what about the unknown? Unknown is the same in direct method and the iterative method, right. You still have to store phi for n cells, right. That is anyway the common between these two. Okay. Also, the computational cost is only order n per sweep. Okay. That means if you do, let us say 50 sweeps, you are doing 50 times n is the computational cost, whereas in the direct method it is order n cube, which is huge. Okay. All right. So, what do? We have to kind of sweep until convergence. Well, we have not discussed what is convergence, but I mean we will discuss it in a little while. So, what we mean is we basically keep updating these values, right. Once you are done from 1 to n, you will again start from 1 to n and keep using these values until you reach an unchanging answer, right. That is what we mean by convergence in this particular context. Okay. So, until we reach an unchanging answer. Now, I am kind of assuming that we are looking at a steady state problem. Okay. If it is transient, we will discuss that later. Okay. So, that is what we mean by convergence, and or unchanging answer, or we cannot really talk about an unchanging answer in the context of floating point values. So, what we say is that we kind of the solution that we obtain between two sweeps would differ by some epsilon. Okay. For example, we have a solution vector that is phi bar, right. Phi bar would contain basically phi 1, phi 2, phi 3 all the way to n. So, this is at a time level t, and the next time level we got phi bar t plus delta t, and the difference between these two in some norm, okay, in some norm would be lesser than or equal to some epsilon. Okay. We will kind of say then that we have reached some kind of a convergence or a steady state. Okay. We will discuss all these things little later. Yes. So, only for the sake of convergence you need to still store these values, only for the sake of this thing. Okay. So, in that context you are storing them, okay, for the sake of checking for the convergence. Okay. Other questions? That is a good question. So, we said we just discussed that we do not need to store, but then we need to store not from the point of view of the algorithm, but from the point of view of checking whether we have reached convergence or not. Okay. Yes. Exactly. So, that is the question we are going to address. Okay. The question is, how do we know that the next iteration it is going to diverge, right? How do I know that I will get some physical values out of it? Okay. So, that is the next point we are going to look at. So, essentially the convergence of any iterative method is guaranteed only when the coefficients satisfy something known as Scarborough criteria. Okay. Okay. So, if the coefficients of the matrix satisfy something known as Scarborough criteria, then the convergence is guaranteed for an iterative method. Okay. Now, this is a sufficient condition. Okay. So, this is a sufficient condition okay, it is not a necessary condition, it is a sufficient condition. That means, even if your coefficients do not satisfy Scarborough criteria, it may still converge, okay. But if it satisfies Scarborough criteria, it will definitely converge, okay. So, that is what Scarborough criteria is. Now, what is Scarborough criteria? Okay. So, we will be making lot of references to this criteria as we go along. So, let us look at it. So, Scarborough criteria says that the absolute values of the neighbors, that is absolute AE plus absolute A west, upon absolute AP. So, essentially we are looking at the absolute values of the coefficients of the neighbors, their sum, okay, divided by the absolute value of the coefficient of the primary cell. Okay. This I can rewrite it as absolute value of NB, where NB I would like to kind of a short term for short form for neighbor, okay, which I will use. So, sigma for all the neighbors, here in this particular case neighbors are east and west, okay, upon mod AP. Okay. So, we have only 2 neighbors. So, the sum of the absolute values of the neighboring coefficients upon the central coefficient should be less than or equal to 1 for all grid points, okay, and should be less than 1 at least for one grid point. Okay. So, that is Scarborough criteria. So, this needs to be satisfied. If this is not satisfied, your iterative scheme may not converge, okay, may not give you a, they are not, it is not a guaranteed to converge. Okay. All right. So, what does this mean? This means that the coefficient matrix has to be in different terms. This has to be, the coefficient matrix has to be diagonally dominant. Okay. That means the terms on the diagonal should be in an absolute sense should be larger than the sum of the all the off diagonal elements, right. Because if you write this in a matrix form, I have some elements and I have a diagonal, right. Let us say this is my diagonal here, then this should be greater than or equal to or greater than 1 for this value here should be sum of all these neighboring values, right. So, this should be much larger than or at least equal to or larger than all the neighboring values. We know that we do not have many neighbors, we have only like 2 neighbors in the context of 1D because everything else is 0, that is why we have this A east and A west, okay, fine. Questions? So, do we need to check for Scarborough criteria before we solve once we discretize our system? Yes, we need to, right, otherwise it will not work, right. We come back and then instead of worrying about it later, we should first check for it and then see whether it is satisfying Scarborough or not, okay. We will do that for pretty much all the discretizations that we will do in this particular course, okay. You can, yes, you can make the matrix. So, the question is, if a particular discretization does not yield a diagonally dominant coefficient matrix, can I still work with this? Yes, you can. There are certain ways with which you can kind of improve the diagonal dominance of a particular system. We will see that little later, okay, with the usage of source terms and things like that, okay. Other questions? Diagonal dominance, okay. So, let us say question is explain the diagonal dominance again. So, essentially what we mean is, for example, I have a set of rows, okay. So, I am looking at the second row, okay. Second row, the first element is off diagonal element, let us say it is 1, okay. This is a diagonal term 2 and this would be 1 0 0. So, this is diagonally dominant because 2 is equal to the sum of the neighbors, right. What about this? Is this diagonal dominant? Yes, it is still diagonal dominant because the absolute value of the central coefficient is larger than this. So, similarly you can have any value equal to 2 or greater than 2, okay, to be diagonal dominant. This cannot be lesser than the diagonal off diagonal element. So, if you have a term which is let us say the next term is 0 minus 1 1 minus 1 0, this is a problem, okay. You will not, if you get like this, then you are not satisfying Scarborough at one cell, okay. Now, this only says that it is not guaranteed to converge, but it may still converge, okay. It is only a sufficient condition. Yes. So, the question is, if we have more neighbors, what shall we do? We have to take all the neighbors, okay. So, for example, let us say we go to 2 dimensions, then our matrix, if you put in the matrix, then you have let us say I am looking at some interior row, okay, where I have this is my AP term and then I have some non-zero terms here. So, I have some non-zero term here which is let us say 1, I have 0 0, let me call minus 1, minus 2, 0, then I have minus 1, 0 0, minus 2, 0 0 and so on, right. then what would be AP? AP should be greater than or equal to 1 plus 1 plus 2 plus 2, right? It should be greater than or equal to 6, right? Sum of all the elements in that row, okay. We will come to that when we do the 2D diffusion equation. Other questions? No, clear? Okay, fine. So, let us have some, kind of few comments on the Gauss-Seidel method. So, few comments are no need to store the full matrix, right. We just need to store only the non-zero elements, okay. So, computational cost is only order n. Fine. So, but if we have a large cells or not large cells, we have let us say many cells in the domain, then Gauss-Seidel is actually kind of slow to converge, okay. It is kind of slow to converge. This is kind of a negative point for Gauss-Seidel, but we will look at few techniques which will accelerate it, okay, accelerate the convergence if we have a large number of cells. For example, let us say you have 100 cells, Gauss-Seidel might work quickly, but if you have let us say 1000 cells or let us say million cells, then Gauss-Seidel will take a long time to converge to within that epsilon, okay. So, as a result, this is slow to converge. We will look at some acceleration techniques later on in the course. These are, one is the successive over relaxation, and we will also look at something known as multi-grid methods, okay. These will help to alleviate the problem of slow convergence of Gauss-Seidel, okay. So, now will you be able to code for a Gauss-Seidel with this discussion or no? Essentially, we have this equation APVP equals sigma all the neighboring terms plus some b, right. We basically have Ax equal to b. All you have to do is you have to go to every cell and then update that cell unknown value, update that cell phi value from the neighboring phi values, which are guesses, right. You could start off with phi equal to 0 everywhere, right, and phi could be specified on the boundary cells. So, we have one discrete equation for each of the cells. Let us say if we have 5 cells in the domain, we have 5 equations. You visit each and every equation and update it, right. And then once you keep updating it in another loop, you would have, you check for is my previous values very different from the new values I have obtained. If it is very different, you go back, keep doing this until they are within certain epsilon, okay. That is all you have to do. So, basically 2 loops kind of, one loop is to go from cell to cell, another loop outside this one would be where you check the difference between these two in an individual manner or in a collective manner, right. We will look at an example problem after that. I think you will get a little more confidence, but that is the philosophy of Gauss-Seidel, okay. Fine. So, let us look at a few concepts that kind of arose yesterday, which was related to accuracy, consistency, stability and convergence. So, let us look at what is known as accuracy. Accuracy is we have defined using the Taylor series expansion, right. For example, if we have d square phi by dx square at certain point I, we had an expression yesterday in the context of finite difference methods, where we wrote it was as phi I plus 1 minus 2 phi I plus phi I minus 1 upon what, delta x square, right, plus we said we have neglected something of the terms order delta x square, okay. This we have called it as what, truncation error, because we are truncating these terms, okay. Okay, this is truncation error. Now, accuracy is basically defined by the truncation error that we have, okay. So, essentially if we have a scheme is nth order accurate if the truncation error is order delta x to the power n. Okay. That means this particular scheme is second order accurate. Of course, now the truncation error or accuracy, the truncation error gives a relative error decrease, or we can say rate of decrease of error. Okay. So, the truncation error term or the accuracy of the scheme you have used gives something known as rate of decrease of error. Okay. So, what does that mean? That means if I employ my truncation error is of the order delta x square. Okay. Now, what will be my truncation error if I take a cell, all the cells in my domain are now delta x by 2, right. If I take, let us say if I have 5 cells, I will make it a 10 cells. Okay. That means each of my delta x is now halved, right, smaller and smaller. So, what will happen to truncation error? It will decrease or increase? It will decrease by 1/4, right. Essentially, it will become T by 4, right. So, essentially if you halve the grid, the truncation error will go down by 1/4 if you have a second order scheme, right. Similarly, if I halve the grid, the truncation will go by 1 by 2 to the power n if I have an nth order scheme, right, and so on. All this is of course assuming the delta x is less than 1, okay, fine, all right. Okay, so what will happen to, so that means my truncation error would go down by 2 to the power n if my order of the scheme is delta x to the power n, right. If I halve the grid, it will go down by 1/4 and so on, okay. Okay. So, fine. So, that is about the truncation error. Now, this only gives the truncation error only gives a relative error, okay, in the domain. It does not talk about the absolute error, okay. So, the absolute error is not indicated. This only tells you if you kind of refine your cells or if you make them bigger, this is how the error that you are computing would increase or decrease. Now, what about the absolute error? How do we check for that? In order to check for absolute error, we should know the exact solution, right. Only then I can check for the absolute error, right. That means if I know, let us say I have found some phi bar in the domain, this is what I computed from my finite volume method. Then if I know what is phi exact, I can go back and then calculate phi exact at those grid points and then find the difference between these two. That would give me something known as absolute error, okay. So, truncation error does not talk about anything related to absolute error, okay. It only tells you as you refine your mesh, your truncation error will go smaller and smaller, and that means you are committing lesser and lesser error, okay. Now, this truncation error is a property of the discretization scheme, okay. So, that means if we change the discretization scheme, instead of second order, if you go for third order accurate, you have the truncation error much smaller, okay. It could be, let us say if we have a fourth order accurate scheme, then your truncation error will be of the order of delta x to the power 4, okay. So, that is why this is a property of the discretization scheme, fine, yeah. Okay. So, truncation error is basically, the question is explain the difference between truncation error and the absolute error. Truncation error only gives you a error in the context of in a relative sense or rate of decrease of error. For example, you take a mesh of delta x size, you make it delta x by 2, then the truncation error goes down by 1/4, right, if we have a second order scheme. That is what it tells you. But if you use a second order accurate scheme and you converge to some solution, right, and that solution is let us say phi bar. So, this is the solution you have converged, this phi bar you have converged to by comparing phi bar with phi the previous time step, okay, let me call it as t minus delta t bar, and you found that the difference between these two is less than some epsilon that you have set. Now, you say that okay, we have reached convergence, but when you go back somehow you know there is an exact solution, okay, you go back and compare this converged solution, okay, with the phi exact, then you realize that there is some error between these two, this could be let us say some epsilon 1, okay. Now, this is your absolute error, fine. One, if you want to take, if you realize that this epsilon 1 is much larger than what you had anticipated, what you would do, you would either go back and change your cell size, you would make it smaller, right, and reiterate and again converge to some value and then you compare again, right, or you could have, instead of decreasing your delta x, you could use a higher order accurate scheme, right, because on the same delta x a higher order accurate scheme will have lesser truncation error and thereby can give you little more accurate result, okay. So, there are two ways to obtain this, one is to keep decreasing delta x or keep going to a higher and higher order accurate scheme on the same grid, right. Of course, both have their own differences and advantages, we will discuss that later. Is that clear? We will probably do this as part of the assignment, okay. We will have an exact solution, we will compare and then see difference between absolute error and the relative error. Other questions please? No? Okay. All right. Then let us move on to the next concept, that is accuracy is done. Then we will look at something known as consistency. So, all these are, we are again looking from the context of overview of numerical methods, okay. We will come back to accuracy, consistency, all these things when we actually do the finite volume method for diffusion, convection diffusion and so on, okay. We will revisit that. Here we are only kind of giving an introduction to what these mean, so that I can freely use them, you know, without you getting doubts in your minds, okay. Essentially, if I say accuracy and truncation error, you will be able to kind of connect to them and we will visit these later, okay. We will use a Taylor series and kind of calculate the particular values, okay. Now, what is consistency? Have you heard of this term consistency? Consistency is used to denote that the truncation error that we have for any scheme, if it goes to, if the truncation error tends to 0, that means it becomes smaller and smaller as your delta x or delta t are made smaller and smaller, okay. So, as you go delta x, refine the values of the delta x, delta t, your truncation error, that is what you expect, right, the truncation error should go to 0. So, the error this should go to 0. Now, how do we know that? We know that from the scheme we have used, okay. So, if a scheme displays this property, then we say that the scheme is consistent, okay. Now, you may have a question, well, all the schemes will be consistent, is not it? Why should we care about inconsistency in this context? It will not be, some of the schemes are not consistent, okay. For example, so what does this mean? This means that your delta x, as you refine it, your truncation error is decreasing, then it is fine. That means you have obtained a solution on 5 cells, you got some solution. Now, you have solved it on let us say 100 cells, you got a solution that is worse than the previous one, right. That can only happen if the scheme used is not consistent, right, that is not expected. So, this can happen if let us say for example, we are not deriving this thing, I am just stating it as of now. Let us say if we take the one dimensional wave equation, 1D wave equation, that is first order accurate, or let us say I will take the transient heat conduction equation, okay. So, I will take the 1D heat equation, okay. So, essentially I have dou phi by dou t equals sum alpha dou square phi by dou x square, okay. If I use a particular method which is known as Dufort-Frankel's method. So, this is a particular method, it has its own discretization way of discretization. Okay, this is a particular discretization which is called Dufour's-Frankel method. If you use this method for the 1D transient heat conduction equation, the truncation error you would get would have terms which will have which will contain delta x square, order delta t square, and order delta x by delta t square. Okay. So now do you see the problem? You see the problem, right? Essentially the first term is fine, second term is fine, but there will be some terms which will have this ratio of delta x by delta t. This is not good, right? That means if you keep refining your delta t and delta x in such a way at the same rate, then this error will remain the same, right? Order delta x by delta t will remain the same, and even though you are refining your delta x and delta t, your truncation error will not tend to 0, right? It will only tend to a particular constant value, and you cannot get rid of that error from your solution. Okay. So, such schemes are inconsistent and we do not want such a scheme. Okay. We will probably do this later on as an example. So, that is an inconsistent method. Okay. Questions? Now, you may ask like why, okay, then why do we care about this method? Like, you know, the thing is it was proposed, it was used, and later on it was found that this is inconsistent method. Okay. That is how this has come about, but there are certain other properties which are useful for this method, that is why it is used, by knowing that this is an inconsistent method. Okay. But we want to work with consistent methods, so we want the truncation error to go to 0 as we refine our delta x and delta t. Okay. Fine. Let us look at something known as stability. Okay. Stability is generally used in the context of iterative schemes, okay, or iterative methods. Any guesses on what is stability? We just said that it is used in the context of iterative methods. Convergence, essentially we do not want the errors to grow from iteration to iteration, right. If the errors remain the same or decrease, then we call a particular iterative method as stable. Okay. So, if the errors remain the same or decrease from iteration to iteration, then we call that method as a stable method. Okay. All right. So, essentially this is a property of the iterative scheme we are employing. Okay. That means this is related to the path to the solution. Okay. That means it depends on the path we are taking based on the iterations. Okay. So, we mean path, basically we are going to a set of intermediate values of phi. Okay. That is the path we are talking about here. So, property of the iterative scheme. So, we want only of course work with stable methods or stable schemes, such that our errors do not grow from iteration to iteration. Now, how do we know whether the iterations are the other errors are going to grow or decrease? There is one classic tool that is known as von Neumann stability analysis that can be applied to simple linear equations. Okay, simple linear equations, simple linear differential equations. Okay, which will tell you whether the particular scheme is stable or unstable and so on. Okay, we will be doing a stability analysis little later after we kind of discuss the diffusion equation. Okay, but if you have real life problems, let us say if you have a coupled nonlinear equations and so on, then the stability analysis is difficult. therefore, it is not much used. Okay. So, we have to kind of work with some linear counterparts of the nonlinear equations we are working with, and then come about with some kind of measures which will hopefully give a solution to our coupled equations and so on. Okay. Otherwise, this gets very difficult to know whether a particular method is stable or not. Okay. So, that is why there are no general methods that can be used for knowing the stability of coupled nonlinear equations. Okay. So, we kind of work with the counterpart equations, linear equations, or with some experience we would kind of guess them. Okay. So, but we will be doing a von Neumann stability analysis later on after the diffusion is done. Okay. Now, we kind of did not see. So, we said the accuracy is a property of the scheme, right? Accuracy is a property of the scheme, and what about convergence? Is convergence also a property of the scheme? Sorry, consistency. So, we said accuracy is a property of the scheme, right? Similarly, we said consistency. What about consistency? Excuse me. Is it also a property of the scheme? It is a property of the scheme, because if we use a higher order accurate scheme, so this is also a property of the scheme. What about stability? Stability is a property of the iterative method, right, not the discretization scheme. So, these are for the discretization scheme. Okay. This is a property of the iterative scheme that we use, or it is basically a path to the solution, right. So, which path do you take in order to obtain a stable solution, right. So, essentially stability is measures the path you are taking. You may take a path which will diverge, then it is not stable, right. It has nothing to do with the discretization scheme you have used. You could use a second order scheme, but if you use an unstable method in the time stepping scheme, then it may kind of not converge. Okay. Now, we will come to the final thing known as convergence. Convergence basically, if you have a consistent and a stable method, okay, then we say that we have a convergent method. Okay. That means we should have a consistent and a stable method to have a convergent scheme. Everything we work with will be convergent schemes. Now, convergence also has different couple of different meanings. One of them is basically obtain a solution that is independent of the mesh. Okay. You might have heard of this term grid independency or mesh independent solution. That is also in some context convergence is used to indicate that the method converges as you take different finer meshes. Okay. And in another context, convergence means that we obtain an unchanging answer, okay, from the scheme. That means converging to an unchanging answer. Okay. So, in this particular course, we will be using convergence in the context of the second one. Okay. That means, if we reach a unchanging answer, that means we say that we have converged our solution. Okay. That is what we use in this particular course, but you would see that people use convergence in the context of obtaining a solution that is independent of the mesh. For example, you have taken 100 cells, 1000 cells and 2000 cells. The solution you obtain from 1000 and 2000 may not be very different. Okay. That means we have converged the solution onto a particular mesh independent solution. Okay. So, these are the four concepts: accuracy, consistency, stability and convergence. All these properties we would make use of as we go along, and also the Scarborough criteria that we have discussed in the context of iterative schemes. Okay. Thank you.